Multivariable Calculus, Lesson 14.5, Day 2, we're going to be doing implicit differentiation. You can see our learning target at the top. I can take derivatives implicitly. And of course, this is very much related to the chain rule. So suppose f of x comma y, a function of two variables, is differentiable. Its derivative would always exist. And f of x comma y is set equal to 0. Y is defining y implicitly as a differentiable function of x, if you think of it that way. Well, if that's the case, you could say, look, if y is thought of as a function of x, just like we did in the earlier lesson, we can say, look, if we're going to take derivatives with respect to x, we can go through two paths. And you can very quickly see what would happen. You'd have partial derivative of f with respect to x. You can see right here it stops at x. Even if you did a dx over dx, guys, dx over dx, of course, would just be a 1. So even if you did that, you'd see you'd just be left with that. And we're taking our derivative really with respect to x in the end right here. We're having our partial derivative of f with respect to y multiplied by a dy dx. And if we're taking our derivative on the left, we get this, but the derivative of 0 with respect to x is also a 0. So, tell you what, I'd like for us to solve for dy dx. And it's not going to be all that difficult. This is just a 1. I'm going to subtract this derivative of f with respect to x. We're going to get this. And then finally, we divide. And very, very nicely. Here, let me write this a little bit higher so we can get this written out nice. We'd have the partial derivative of f with respect to x with a negative out in front of it. And this right here is our formula. We could write it a little bit nicer, and in fact, I really like to write it in a shorthand way without having to use delta. Imagine this, we'd have negative derivative of the function with respect to x all over the derivative of the function with respect to y. I want you to notice something real quickly because we're going to see this repeatedly today. Look at this. dy, you have the derivative of f with respect to y down below. Likewise, if we were to take a look at this x right here, here's your dx. We always will have a negative out in front. Pay attention to this right here. This is going to be phenomenal. We're going to see this pattern continue to emerge even when we look at more complicated problems. So let's take a look real quickly at this next example. Find dy dx of the following implicit function. In other words, they're telling you in this regard, think of y as if it were a function of x. Here's what you did last year in single variable calculus. You would go ahead, you take your derivative all at one step. The derivative of x squared, that would be a 2x. The derivative of sine would be cosine. We'd have the cosine of y, but y is a function of x, so we do the chain rule. We'd get dy dx. And then the derivative of y would just be dy dx. And not like this is a super hard problem here. You've done this countless times, in fact. I tell you what, you'll see a dy dx occurring twice here. I'm going to factor that out. And that's going to leave me with a cosine of y minus 2. Simultaneously, I'm going to subtract a 2x. And it's not like this is a hard problem. We're so used to doing it this way. You can say, hey, look at this. We get our negative 2x all over the cosine of y minus 2, and we're good to go. But I want us to take a look at this problem in our new perspective, what we just talked about. Imagine that this function on the left side of the equation, that's f. And we could say, well, take your derivative with respect to x, if that's what f is. Well, what do we get? Plain and simply, just a 2x. Everything with a y is considered to be a constant. How about we take our derivative with respect to y? Well, if that's the case, the derivative of the sine of y would be the cosine of y, and then we'd have a minus 2. But what did we see up above? We saw that dy dx would be the opposite of the derivative of f with respect to x all over the derivative of f with respect to y. Look at that. You get the same exact thing just real quickly. Very nicely. It's a brand new perspective, a brand new way to look at these problems. Well, let's just take a look at a more complicated scenario. Let's just say that we have a function z, which is a function of x and y, and we have a capital F, which is a function of x, y, and z. Set it equal to 0. That function defines z as a differentiable function of x and y. And wow, tell you what we can do. We can take a look at that function f and say, well, we've got x, we've got y, we've got z, but z is a function of x and y. So tell you what, we're going to take our derivative with respect to x, but what I'd really like us to do is eventually see if we can find the partial derivative of z with respect to x. So we're going to take our derivative with respect to x here. And this little tree is really going to help us out. You can most definitely get a lot of help from it. And let's just see, we'll magnify that up again. But let's see here. If we were to just, branch this out right here, branch this way, and then come this way, you can think, what about y? Even if you thought about y for a second, it's not a function of x. We can still work this all out. Let's just see where we're going with this. As we're taking the derivative of capital F, we'd get partial derivative of f with respect to x. Even if you wanted to look at the derivative of x with respect to x, that's just going to become a 1. If you wanted to take your derivative of f with respect to y, well, you could. It's just that dy dx would be a 0. That's going to wipe out. And then we'll have our partial derivative of f with respect to z, but then we'd have to multiply that to the partial derivative of z with respect to x. And don't forget there's a right side of this equation. Here we just get a 0. So in the middle, this is going to disappear. And tell you what, I'm going to bring this partial derivative of f with respect to x on the right side. When we change sides. And wow, we're almost there. To find and solve for the partial derivative of z with respect to x, I want you to see what you get. It's going to be the partial derivative of f all over the partial derivative of x all over the partial derivative of f with the partial derivative of z. Now, another way we could write this is to say that the partial derivative of z with respect to x would be negative f sub x all over f sub z. And notice the pattern that we were picking up earlier. We saw up here, look, dy, and down below we had f sub y. Well, look, partial z derivative with respect to z. Down below, Sorry, having some trouble with my highlighter. You'd have x and x. And guys, that can be so helpful where in the future you're going to be able to do this more quickly. Case in point, if we were to come down over here, and if we were to say, hey, same problem, could we find the partial derivative of z with respect to y? Well, following what we just saw up here, and if we were to follow that pattern, you would guess that it would be negative derivative of f with respect to x all over the derivative of f with respect to z, and it is. In fact, that's exactly what you're going to have. So that hopefully is going to truly help you out significantly. Let's take a look at, say, just one last problem. Here is your capital F of x comma y comma z, and you know what, let's just get started by taking a derivative of f with respect to x. As you do that, you'll get 3x squared, and then y cubed and z cubed are 0. Here you'd be left with a plus 6yz. Your x right here just goes away. How about your derivative with respect to y? Well, it's going to look amazingly close, won't it? It's 3y squared. The x cubed and z cubed have derivatives of 0. And then we'd say plus 6xz. Finally, we could say, what's your derivative of f with respect to z? Well, we'd get a 3z squared plus a 6xy. Well, guys, we're almost done. First, they're saying, can you find the partial derivative of z with respect to x? Well, guess what? That's going to be negative derivative of f with respect to x all over the derivative of f with respect to z. And again, it's that pattern that we were talking about earlier, where I hope it's really clear as day to you. All you got to do at this point is plain and simply plug everything in and work it out. So you'll have a negative 3x squared plus 6yz. Down below we'll have 3z squared plus 6xy. And if we divide everything by 3, which can be done pretty quickly, divide every single part, or similarly multiply, distribute a 1/3 over 1/3. This would be the partial derivative of z with respect to x. Similarly, if they said, what's your partial derivative of z with respect to y? Well, I hope you could take a guess. It's going to be this. The opposite of your derivative of f with respect to y, all over your derivative of f with respect to z. By the way, we'll have the same denominator. I think you can see that very quickly. And then your numerator now is just going to be a negative with this 3y squared plus 6xz. And very much the same issue. Divide out a 3 everywhere, and you will be in business fast. You can see we are wrapping this all up. And guys, that's all for this section.